Okay, in this video, I would like to talk about stoichiometry. Stoichiometry is one of those chapters that can be very, very difficult and challenging for some folks, but really, I think the difficulty comes from it's a culmination of a lot of different chapters come together in this one, and that's can be what makes it difficult, and it's also somewhat based in math, which can be intimidating for some folks. But really, I'm going to try and break it down, and I don't think it's very bad at all. The word stoichiometry in and of itself sometimes can seem a little like, what is this all about? Stoichion, this is a Greek word. Stoichion means element, metry means measure, so you're measuring the elements. And basically what we're going to do is we're going to say, listen, if you have a certain amount of this material, or this material, how much of this will be produced? Or if I have a certain amount of this material, how much of this do I need to make this? And so you're just relating the amounts of the elements to one another. So if you basically look at an equation, what this is basically saying here is that I've got H2, and you could draw it like this. Let me let me make that pencil line a little bit thicker. So if this is, these are my H2s, and then let's say that my oxygen is here. Here's my O2. As this reaction goes forward, I'm going to make two H2Os. And so, here's maybe an O with some H's. Here's another O with some H's. And so if you're visually looking at this, two molecules of hydrogen react with one molecule of oxygen to produce two molecules of water. And if I put X's in the hydrogens to distinguish them from the oxygens, it would look like this. You would see four hydrogens on the left side of the arrow, four hydrogens on the right side of the arrow. Here are my two oxygens, here are my two oxygens. So everything balances out. But what I can do, and again, we're talking about amounts here, I could say, well, rather than two molecules, let's say I have 24 of these. Well, that would react with 12 of these to produce 24 of these. I'm just scaling up. The number of molecules of hydrogen is always going to be twice the number of molecules of oxygen. The number of molecules of water is always going to be twice the number of molecules of oxygen, and the same as the number of molecules of hydrogen. It's 2 to 1 to 2. And this is where my coefficients come into play. And again, if I'm dealing with single molecules, it would be 2 to 1. If I'm dealing with a dozen molecules, it would be 2 to 1. But more often, what I'm dealing with in chemistry, is the mole. So basically, I've got 2 moles of this combining with 1 mole of this to produce 2 moles of this. The ratio is the same. Remember, a mole is a specific number. It's 6.02 times 10 to the 23rd. I'm sorry, I forgot to raise this as an exponent, but that's times 10 to the 23rd. So this is basically saying if you have a specific number of this, you'll have half that number of these. So if I have, as an example, let's say I had 4 moles of this. How many moles of this would I need? It'd be 2 moles. And how many moles of water would I get? I'd get 4 moles. So the relationship holds up. Let's say I had 3 moles of hydrogen. How many moles of this would I need? It would be half that, so it would be 1.5 moles of this, and I would get 3 moles of water. So you see the relationship is always 2 to 1 to 2. That's what stoichiometry is basically dealing with. So if I were to do a problem with this, the problem might look something like this. You start with 3.5 moles of hydrogen. How much water will come out? Well, what I would do is I would just look at my ratio and say, and again, if you follow dimensional analysis or factor label method, I have 3.5 moles of hydrogen. I'm going to do times in a line. Whatever unit you have here, I need to cancel, so I'm going to put that down here, and in this case, I'm going to moles of water, H2O. And what is my relationship? Well, for hydrogen, it's 2, and for the water, it's 2 as well. So basically, and it makes sense, 2 moles, it's the same. So if I start with 3.5 moles of this, I'm going to get 3.5 moles of water as well. So again, that relationship holds because my moles of H2 cancels. My final units would be moles of H2O. I could also figure out how many moles of water would I need to react. Let's say I have 6.2 moles, and I'll use just a slightly different variation here because that's molarity, capital M. Let's say I have 6.2 moles of hydrogen. How many moles will I need of oxygen to react with that so the whole thing goes to completion? Well, again, if I put moles of H2 here and I go to moles of O2, what's my relationship? Well, for every 1 mole of O2, I need 2 moles of H2O. So if I do my math, moles of H2 cancels, and if I start with 6.2 moles of hydrogen, it will react with, divide this by 2, 3.1 moles of oxygen. And again, there's your answer there, there's your answer there. And this makes sense because notice that the number of moles of oxygen is half that of hydrogen, so I basically just divided this in half. So that in and of itself is basically what stoichiometry is all about. It's just comparing the moles of one thing to moles of another. What can complicate this, of course, is you're not always given moles. And in a laboratory situation, rarely do we know moles. We have to measure that. Well, a couple of things that we've done in class that allow me to relate moles to other things is if I'm dealing with numbers of things, atoms, molecules, formula units, of course the number of things in a mole is 6.02 times 10 to the 23rd. You can deal with a molar mass off the periodic table, and again for that you would just simply look and get that off the table, and that's the mass in grams. So anytime you're given grams, you simply convert using the molar mass to moles. If you're dealing with gases, a common thing is when you're at STP, which is standard temperature and pressure, that's 0 degrees C and 1 atmosphere of pressure, or 273 Kelvin, the molar volume of any gas is 22.4 liters. So what oftentimes happens here is you end up with a situation where you have to take one of these sorts of units, turn it into moles, then relate moles of one thing to moles of another, and you can do your problem. So let's just do one of those. As an example, let's say I had some hydrogen gas, and let's say I knew its mass in my lab. I'm working with it. It happened to be, oh, I don't know, let's call it, let's say we had 5 grams of hydrogen, just to pick a number. If I know the mass, I can't relate the mass of hydrogen to the mass of anything else. I need to turn it into moles first. So what I would do is go from grams of hydrogen to moles of hydrogen. And this relationship is 1 mole of hydrogen is, and again the molar mass of H, if you look in your periodic tables, approximately 1.0, but I have 2 of them, so it's 2.0. So if you do your math here, that now 5 divided by 2 of course is going to give me 2.5 moles of hydrogen. Well, now I can relate that to anything else. If I said to you how many moles of water would be coming out, well of course that's going to be 2.5 moles of water. If I said how many moles of oxygen are needed, it would be half that, which of course would be 1.25. So I can then convert that, and let's say you got as your answer, let's do the oxygen as an example. Let's say I said to you, well, how many moles of oxygen or how many grams of oxygen will be needed in this reaction? Well, I know that if I go from moles of hydrogen to moles of oxygen, we know that the relationship is 1 mole of oxygen for every 2 moles of hydrogen. So if I did my math, my moles of hydrogen will cancel, and I will need half of this number, which of course is 1.25 moles of oxygen. Okay, that's how much oxygen is needed to react. Well, and again, from a realistic standpoint, in a lab, I may not want to know moles. I may want to know how many grams of oxygen would be required. So again, I can use my conversions here. So I can go from moles of oxygen to, say, grams of oxygen. And again, if you look on your periodic table, oxygen is 15.999, or approximately 16. I have 2 of them, so it would be 32.0 grams per 1 mole. So then if you just do your math, excuse me, that's going to be, was that 40 grams, if I'm doing my math correctly, that will be 40.0 grams of O2. And so then what I've done is I've now said, listen, if I start with 5 grams of hydrogen, I've now predicted how many grams of oxygen will be coming out by taking what I was given and first of all turning it into moles, relating the moles of one thing to moles of something else in the equation, and then relating that to the moles, I'm sorry, I said come out, this would be what I would need of another reactant. I could also predict the amount of water by doing the same sort of a process. Now of course I can do this in one step, and that's what I want to show you here. The bridge, the main part of this, it's almost this bridge going from moles of one thing to moles of another, is always the key. If you will always take the moles of what you start with, and I'm going to do start, and then put moles of what you start with here, and put moles of, I don't know, I'll call it destination. Whatever the thing is you're trying to find. It could be a product, it could be another reactant, it doesn't matter. But basically I'm relating the moles of what I started with to the moles of what I'm trying to find. And these are coming from the coefficients. So these are the coefficients, that's these guys right here. So this is all coming from the coefficients in your equation. Now, if I'm give you moles at the beginning and ask for moles, that's all you need to do. The problem is, or not necessarily a problem, but the thing you have to deal with is oftentimes you're not given moles. In a lab situation, most often you'll be dealing with maybe a volume of a gas or grams of a material, grams of a gas. If that's the case, what you need to do then is turn it into moles first. So let me do that in a different color. So let's say I was given grams or atoms or liters as an example. What I would have to do first is take the grams, atoms, or liters of what I start with and basically divide that by the conversion. And again, if I was given grams, that would be molar mass. If I was given atoms, that would be 6.02 times 10 to the 23rd. And if I was given liters at STP, that would be 22.4. So if you are not given, if you're given moles at the beginning, you start right at the blue. You go from moles of what you're given to moles of what you're trying to find. If you're given grams, liters, or atoms at the start, you have to divide by the molar conversion, then go to the moles of what you began with, and then go to moles of what you're trying to find at the end. Now let me use another color for my final thing, or my destination, whatever that is. And again, if all I want at the end is moles, I'm done here. But let's say they don't want that. Again, I'm going to go moles of my destination material, and I will turn that into grams, liters, or atoms. And again, grams would be the molar mass, liters would be 22.4, and the number of atoms, if I had to get that, was 6.02 times 10 to the 23rd. Now these conversions are always per 1 mole, so you would have a 1 there. And again, with the other side of this, this would be 1 mole, because it's always 1 mole is the molar mass, or 1 mole is 6.02. So that really the things you need, or what you start with, always start with that, divide by the molar mass to get the number of moles, and that's always a 1. Then you can go from moles of what you're going starting with to what you're trying to find. That comes from the coefficients in the balanced equation. I'm going to put little boxes there, and I'll put coefficients. Okay, there, and then down there. And so those are the coefficients from your equation, and then a 1 goes here, and then you will get your answer. And again, you don't have to solve for the product. You can solve for anything along the way. All right, I hope this is helpful to you. Next, I will do percent yield based on this sort of a problem.